Hello everyone, this is week 5 of NPTEL course Introduction to Algorithms and Analysis. In this week, the primary topics that were discussed were hashing and hash functions and open addressing, universal hashing, perfect hashing, and binary search tree sorting. Like uh, we had started discussing about binary search tree sort, and we did a bit of time complexity analysis of binary search tree sort. So what we'll do in this session is we will directly take up some of the example problems, and then we'll discuss the theory also within those examples as required. So let's just start with the first one. So using division method in a given hash table of size 157, the key of value 172 is placed at what position? So what we have been given is that we have a hash table, right? And the size of the hash table is 152 or 157, right? There are 157 different hashes that we can make basically using division method in this. And we want to know the key of the value 172, right? Basically, uh, where will the value 172 be placed? Like at what position from 0 to 156 index? What will be the index for the value 172? So let's make this horizontal so that we don't waste much space, right? So from 0 to index 156, we want to know the position of value 172. So in division method, how do we get the basically what's the hashing function? Uh, what's our h of k? It's k mod m, right? Where m is the size of the hash table. Okay, so in this case, k is 172 and m is 157. So the key basically for 172 will be 172 mod 157, right? And that turns out to be 15, basically, right? So the value 172 will be at the index 15th in this, right? And this is assuming that there is no collision right now in this hash table, right? That this is the first element that we are inserting in the hash table. So we don't need to think about what kind of probing we are using in if we have a collision or what. We assume that it's an empty hash table and this one has to be placed at whatever the index hash function gives us or whatever the key the hash function gives us, right? So we just need to remember that for division method, the hash is calculated, like the key is basically calculated using the modulo operator, right? Just a single uh, division. Let's take another example. Consider a hash table of size m equal to 1000 and a corresponding hash function h of k is the floor k times a modulo 1, where a has a value of square root of 5 minus 1 by 2, right? Then what is the location of key k equal to 61, right? So in a hash table of size 1000 and a given hash function, what is the location of the given key? So what we need to do is we just need to basically evaluate the hash function, right? So um, k is 61, m is 1000, and a is given to be square root 5 minus 1 by 2. So h of 61 is 1061 square root of 5 minus 1 by 2 modulo 1, and then floor of that. So this gives us 1000 times. So if we evaluate this, 5 minus 1 by 2. 37.7000733 and so on, modulo 1 floor, right? Let's further simplify this. So this quantity modulo 1 will be basically just the fraction part. 733. Seven zero zero dot 0733. And if we finally apply the floor operator, we get 700, right? So the location for key 61 is 700, right? So uh, of course, like, it is assumed that this hash function is uh, complete, and basically it won't give values outside the range of the table, right? And we can see that, of course, for the given value of k, like for any given value of k, this value inside, right? So this is m times ka modulo 1. So this is modulo 1. This will be always less than equal to 1, not even equal to 1. It always less than 1, this value. So and this is 1000. So this value inside will be 1000 multiplied by less than 1, right? So this complete value will always be less than 1000, right? So these are just some sanity checks that we should be able to do, or we should be able to look at when we are dealing with hash functions, newly given hash functions. Let's take one more example. Consider a 13 element hash table for which f of key is key mod 13. Is used with integer keys, right? So this is basically a function of type h of k is k mod m, right? So basically we are dealing with uh, division method for hashing here, right? So we'll just keep that in mind. Assuming linear probing is used for collision resolution, at which location will or would the key 103 be inserted if the keys 661, 182, 24 and 103 are inserted in that order? Okay, so if we add these keys in a hash table containing 13 elements with a hash function, that is the division method of hashing. If these values are inserted in this hash table, then where will this 103 end up? Right, so let's try to write the solution for this. Okay, so this is our 13 element hash table. Right, now this is empty for starts, and now we have to add these values. Right, we need to start by adding 661. So k is 661. Right, so what will be h of k? It will be 661 mod 13. Right, and what is 661 mod 13? It's 11. Right, so 661 is placed at position 11. Right, so this is done. Next key is 182. Right, so what is hash of 182? So 182 mod 13, that is, oh, by the way, since these are like we want to write indices, so we'll write them in form of indices rather than positions, right? Because what we get from the hash function is the index and not the exact position, right? So this 11 here, that is the index, right? So 661 will be here, right? And for 182, the index is 0. So 182 ends up here. And then for k equal to 24, h of 24 is 24 mod 13, that is 11, right? So 24, so 182 went to index 0 and 24 should go to index 11. But now there is a collision, right? Because 661 is already at the index 11. So for collision resolution, we have been told to assume linear probing, right? So we basically start looking for the next empty place after the index 11, right? So what's the next empty place after 11? That is 12. So 24 goes to position 12, right? and now we have 103, right? What's the hash for 103? That is 12, right? So 103 is supposed to go to index 12, but now index 12 is already occupied by 24, right? So again, we assume linear probing, right? Let's just mark it properly, right? In case of collision resolution, we need to do linear probing. So we go to the next available slot and check if it is empty. So what is the next slot after 12, right? So that is 0, right? We check at 0. Now 0 is also occupied, right? So we check the next available slot, that is 1. 1 is empty, so we place 103 here, right? So you wanted to place 103 here, but it finally went at index 1. So what is the so location of 103 after all insertions is 1, right? It is at index 1. Okay, let's take another example. Suppose you are given the following set of keys to insert into a hash table that holds exactly 11 values. So basically, I'm equal to 11 here, right? And what are the what's the set of keys? 113, 117, 97, 100, 114, 108, 116, 105, and 99. So what will be the positions of these keys when all the keys have been inserted using linear probing, right? So for collision, we have been told to use linear probing, and since we have been just told that this hash function holds exactly 11 values, so m is equal to 11, and let's just assume division hashing, right? Division method for hashing, since we have not been like told anything specifically what to use. So let's let's start with um, wait. Okay, so this is our table. Okay, so let us start uh, inserting values one by one, right? So for k equal to 113, h of k is 113 mod 11, and that is 3. So 113 goes to position 3. Right, I'll stop drawing the arrows now. 113. The next one, 117. Right, so h of 117 is 117 mod 11, that is 7. Right, so this goes to index 7. For k equal to 97, h of k is 97 mod 11, and that is 9. Right, 97. Next is 100. H of 100 is 100 mod 11, that gives 1. So it is 100 at position 1, right? Because it is empty. Now 114. 114. The key for 114 is 114 mod 11, that is equal to 4 for the slot at index 4 is empty. So 114. And then k equal to 108. Hash for 108 is 9, right? But 9 is already occupied. So in case of collision, we use linear probing. So the next empty slot is index 10. So in 108 goes at index 10. Then we do it for 116. H of 116 is 116 mod 11. That is equal to 6. Slot at index 6 is empty. 116 goes at slot 6. Right. The next value, the next key to check is 105. H of 105. So 105 mod 11 is equal to 6. This is also equal to 6. But the slot at index 6 is occupied. So we do linear probing. We search for the next one. 7 is also occupied, so we search for the next one and we end up at 8, right? 8 is empty, so we can put 105 at index 8. And then for the last one, 99, hatch of 99 is 99 mod 11, that is 0, right? Because it's perfectly divisible. So 99 goes at index 0, right? So all the numbers have been placed in the hash table. Now, what is the status of the table after all the numbers have been put? Is basically we have 99 followed by 100 followed by a blank, an empty slot. Then we have 113, 114 followed by another blank slot, and then 116, 117, 105, 97, 108. Right, so this is the final state of the hash table after the insertion of these 9 elements using division method for hashing and assuming linear probing, right? So these were all like basic examples of hashing using division method and using linear probing for collision resolution. Let us do one example with um, chaining instead of linear probing, right, for collision resolution. So let's take the example of consider a hash table with 9 slots. The hash function is h of k is k mod 9. So basically, we are told to use the division method. Right? We are given the division method of hashing. The collisions are resolved by chaining the elements, right? Not linear probing this time. The following 9 keys are inserted in the order, like in 5, 28, 19, 15, 20, 33, 12, 17, and 10. Right, so what are the first or let's just write it here. Maximum maximum chain length to minimum chain length, and third, average chain length in the hash table. Right, so we what we'll do is to solve this, we'll again make a hash table and for the given hashing function, we'll start inserting the values one by one. So for k equal to 5, the hash is 5 mod 9, that is basically 5. And for k 28, 28, 28 mod 9, that is 1. Just a second, I need to put the tablet on charging. Okay, so 5 goes at index 5, 28 goes at index 1. So next 19, h of 19, 19 mod 9, that is also 1. So 19 is chained with 28, like not with 28 but at index 1 it is chained. And then for k equal to 15, 15 mod 9, that is 6, 15 goes here, 20, 20 is 20 mod 9, that is 2, so 20 goes here, into 33, h of 33 is 33 mod 9, that is again 6, so 33 is chained at index 6. Right now, after 33 we have 12, so h of 12 is 12 mod 9, that is 3, so 12 is at location 3. For k equal to 17, 17 is 17 mod 9, that is 8. 10, h of 10 is 10 mod 9, that is 1. So we have another chain at that place. And now we have exhausted uh, basically all the remaining options, right? So now essentially, what is the maximum chain length in this? It is a chain of 1, 2, and 3, like 3 elements, right? So for the first part, maximum chain length is 3. For the second part, the minimum chain length, right? So there are of course empty slots in this hash table, and they represent the minimum chain length of 0 elements, 0. And then the last one, that is what is the average chain length, right? So for average, what we do is we sum all the chain lengths and then we divide it by the total number of uh, total number of slots, right? So what is what will be the value, because again, since we had 9 elements, there should be in total, like, because like all of these should total up to the number of elements that have been inserted, right? So this is 9 over 9 equal to 1. So that is the answer of our third part. Like, what is the average chain length? Average chain length is 1 and should be 1 if the number of elements inserted is equal to the size of the hash table. If it was more than the size of the hash table, the number of elements, then the chain length would be average chain length would be greater than 1. Okay, let's take one more example. Given an open addressed hash table with load factor alpha n over m less than 1, what is the expected number of probes in an unsuccessful search, or what is the expected number of most probes in an unsuccessful search, right? So uh, I think this was discussed in the lectures as well, and we'll just go through the same uh, argument and mathematics here, right? So since alpha is less than 1, it means we have more number of slots than the number of elements that we need to fit, or the number of keys, right? So what is the expected number of probes, like the total number of expected probes for inserting all the n elements. So at least uh, one probe is necessary, right? And then all the subsequent probe, right? Or we can say that for the worst case that at least one probe is necessary, and with a probability of n over m, we hit a slot that is already occupied, right? So therefore, another slot is necessary, right? Basically, another probe is necessary for in search of a next available slot, right? So in search of the next probe, we again at least do one more probe, and with a probability of n minus 1 over m minus 1, we repeat the process. 2 over m minus 2. Um, so, and it goes up till we exhaust all the available all the available slots. Right? We just go over all the slots in the hash table. Right? So now this entire value is less than equal to if at every time we had we were doing it with a probability of n over m, right? Because it will be less than this because yeah, let's leave it here, right? Because like we can just write like this. So this quantity that is our expected number of probes will be less than this. Like this is the upper bound. Okay, so now n over m, we know that we have defined it as alpha, right? So 1 plus alpha, 1 plus alpha, and so on, right? 1 plus alpha. So this is 1 plus alpha squared plus alpha cube plus alpha to the power, like whatever, like up to infinity, right? Because again, we are assuming that it is arbitrarily large, n and m. So this is so now this is basically a geometric series, and its value, it's a power I, and the value of this is 1 over 1 minus alpha, right? So for a given load factor of less than 1, expected value of most number of probes is 1 over 1 minus alpha. So I think all these problems will help you in doing this week's assignment, and I think I'll stop the meeting here and see you guys next week.